So it appears to have dropped again. Oh man. Are we back? Okay, so I'm not sure if the stream is working. It says that it's working on my end, but I can't seem to monitor the live side. So, shoot. I'm gonna try talking to everybody on Teams here. Is if somebody could reply on Teams if it's working. Ah, ah! Okay, I'll try and keep an eye on both Teams and uh, the stream. I don't know what's going on today. Um, like I said, I appreciate your patience. I don't know. We were doing so well, and, and now we're having all kinds of problems. God. Okay, so are you able to see the stream? Yeah, maybe it's my internet. I don't know. Are you able to can people give me a some say something in the chat and I'll just verify that we're up. Okay. Okay. Sorry about this, guys. I'm gonna be messing with this today and just see if I can figure out what the deal is. Um, so if I'm on, at weird times, appearing at weird times, that's what's going on. I'm gonna try and debug what's going on. It's been so stable the last couple weeks. Maybe there's an increase in demand. Maybe it's issues with my internet. I don't know. So But I'm sorry that that kind of upsets everything. Okay, to try and reorient ourselves, we're talking about friction today. And we had talked about this in labs, so there's not a ton of new ideas. The fundamental relationship that we're making use of is the fact that the force of friction is proportional to the normal force. And this is why we care about the normal force in large part. Um, and this is, I want to emphasize this is an empirical relationship. So it's a pretty, it's an observational thing. It's not based on some fundamental, more fundamental law or relationship. It's more of an observational thing. It's also, it depends on material properties and their preparation. Um, and kind of a key thing is that it's always going to resist uh, motion. It's always going to slow things down. It's always going to keep them from moving, etc. Um, so yeah, how does air pressure impact friction? So that's an interesting sort of similar question in that you can think of, um, the air pressure changing the thickness of the air. And so if you're talking about the related idea of like air resistance, you're going to have more air resistance if you're closer to sea level than you would at high altitude because there's more air and so there's more air pressure. So that's kind of an allied subject. For this purpose, as far as what we're concerned in section 5.1, we're just talking about friction between, objects. It'll fit more in line with what we've been talking about so far in terms of blocks, resting on a substrate, and how does the addition of friction impact that. We had talked in lab about how there's two varieties of this constant. There's the kinetic version, which is basically, you can think of this as sliding. And then there's the static version. So the static version is what we looked at in lab, and that's the not sliding case, in other words. And a useful kind of cartoon, I know we talked about this in some sections, but maybe not all, is this graph where you look at the force of friction as a function of like the pushing force. If say you were pushing an object, so imagine you push on it, a block on a floor or whatever. Uh, if you're pushing with sufficient, it's a small force, it's not going to move because there's going to be a small force of friction that's pushing back. And then as you push harder and harder, this force of friction is going to grow until eventually it's going to start to move. And when it starts to move, the force of friction is actually going to drop because the kinetic friction is always less than the static friction. So there's different examples you can think of with this, but for example, it's like imagine you have a bolt that's stuck or something, right? You really have to wrench on it to get it started, but once it's started, then you may be able to kind of keep it moving. So it's an example of how the kinetic friction is actually less than the static friction. And I'm sure you can think of some other examples kind of in that vein. So um, conceptually, this is pretty straightforward. Uh, and really the question becomes, how does this impact solving problems? And this is really the thing that we wanted to exercise by looking at some examples. So Oh, the other thing that I can add for you is, let's see, why is this? Uh, the other thing that I can add for you is there's a pretty useful chart in your textbook that gives you some coefficients of friction for different surfaces, and it also allows us to look at how the static friction is larger than the kinetic friction. But it gives you some examples like wood on wood, ice on ice. So you think of ice as being slippery, so its coefficients of friction are quite small. Like look at the kinetic friction for ice. It's quite a small number. Um, Things like rubber on dry concrete, this has a large coefficient of friction, which makes sense. You want to have traction between tires and the roadway. Um, and you can see like, oh, if it's raining, then that coefficient of friction decreases, for example. So you can see how this would be relevant for different situations that we encounter, driving, for example. Um, and also, I know some folks are, biomedical engineers. It's interesting. This has this chart, the last row. So it mentions, the joints, like cartilage. That lubricated cartilage joint has very low friction, which is not surprising, right? So nature has engineered a very low friction joint in people and animals and everything. So this gives you just some numbers that we can then use in problems, and we'll make use of that straight away. So, okay, let's talk about some examples here. So let me paste an example. So, oops, come on. Sorry, can't get it to paste where I want. Okay, so let's look at this example. We looked at this example before without including friction. So what we're going to do is review that because the block on a plane is a system that I know will cause some students some confusion. So we're going to review this and then add in friction and see the consequences of this. So, okay, sorry, I'm a little rattled with our thing not working. So if we were looking at this situation without friction, we would, the first thing that we would do, we would give ourselves a diagram. We would note that mg points straight down, the normal force, so that we're drawing our free body diagram. The normal force points perpendicular to the surface, and then we had to break this. Let me draw this a little bit bigger. Oh my gosh. Mg points straight down. We had to break this then into components along the ramp, which was mg sine theta. This is theta. And then also perpendicular to the ramp, mg cosine theta. And then how we proceeded from there was we looked at the sum of forces in both x and y. So before, the sum of the forces in y gave us the normal force minus mg cosine theta equals MAY. Now this was 0 because it wasn't accelerating perpendicular to the ramp. And this allowed us to make this statement that the normal force was mg cosine theta. And then in the x direction, when we sum the forces, we have mg sine theta um, equaling mass times acceleration in the x direction, and we could find that the acceleration in the x was g sine theta. And so this was our relationship for without friction. Okay. And this would be similar to the exercise that we looked at in lab. And we could do things like, well, if we know the acceleration, we could do part B here, where if we know how far it starts up, and we looked at this this question before, we could figure out its speed at the bottom by using our relationship that doesn't involve time. Now, what we're going to add to this is friction. So if we include friction, let me draw it in a different color. So the ingredient that we're adding is now, as this is sliding down, there is going to be the force of friction that's going to prevent it from moving. And we're going to have to make some additions to our sum of forces in the x direction. So if we look at that, I'll draw it over here. Now, if we include friction, let me change back to black here. The sum of the forces in x, we're going to have mg sine theta as we did before. Whoa. And now we're going to have resisting that the force of friction. And that's again going to equal mass times acceleration in the x direction. So what is that force of friction? Well, as I stated before, this is mu times the normal force. We know the normal force from here. So the force of friction is mu mg cosine theta. We can put that in here. And notice that the mass will cancel in this question, or in this scenario. And in lab, we use this to solve, the angle at which the max angle, and related that to the coefficient of static friction. Now, in this situation where we have kinetic friction, we can find the acceleration based on this. So let's see. Let's ask a couple questions. So yeah, so the lab connection here was, we could solve this for the max angle where the acceleration was 0. And when we did that, we came up with this relationship that mu s was the tangent of theta. And we could use that to come up with coefficients of static friction. So the ingredient that we're adding now is, well, like, what if it's actually moving? It started moving. And so in that situation, the acceleration is not 0. So we can't do what we did for the static friction lab. And instead, what it would be, right here. Let me just rewrite this. And actually, this is the only accelerant. Let's just call it A. And we can factor out this factor of G if we want. Okay. And I should be careful here. Let's make this mu K. Okay. Okay, so for example, so this would be, the analytical expression. And we can ask questions like, for ice, say, suppose we had a block of, a block of ice, and we wanted to look at this. What would the acceleration be? So we can look up what the mu k for ice on ice is. So we'll refer back to our chart here. Ice on ice, 0.03. Okay. So if we then put that number in, oh, and I should say, for this example, we were working with, this theta was 22 degrees. .03 times cosine of 22 degrees. And we could evaluate this, and we would find that the acceleration of ice on ice would be 3.4 meters per second squared in the I hat direction. Now, this more complicated model that incorporates friction, we can always compare this to the case where there's no friction. So let's compare to no friction. So this 0.03 would become a 0, and we would recover just g sine theta, our old expression that's getting to be familiar at this point for a block on a ramp. And if we evaluate that, we would find that this acceleration for the no friction case was 3.7 meters per second squared in the I hat direction. And so this is a little bit larger, and that's basically what we expect because, of course, the case without any friction is going to have a little bit larger acceleration. Friction is only going to subtract. It's going to keep it from going as fast, or as accelerating as much. Okay, so that was a little sort of the simplest, or a very simple incorporation of kinetic friction into this framework that we've used. We talked a little bit about static friction in lab, and now we've added to this kinetic friction. So let's take a second. It looks like there's some chatter about, is it not working very well? Buffering issues. I'll check my internet on this end and see what's going on. Maybe my internet is slow or something. Let's see. So are there questions about this question in particular? Oh no. Ah, did it drop again? Are we still good? Are you able to see me? I can't tell if the stream dropped again or what. It's not dead, it just had a moment. Ah, well, sorry. Yeah, sorry today. Yeah, I'll try, I'll work on debugging this today. So let's see. Question. Uh, will kinetic be given? It depends on the problem. You could imagine problems where you could have an acceleration and then they would tell, they might ask you to solve for the kinetic friction. Other questions on kinetic friction? Here, I can show you another quick, sort of simple example. Let me see if I can find it here. So this one gives us kind of a chance to uh, connect what we had been doing before. Um, so some of this is stuff without including friction, and some of it is new. Um, oh, did it just drop again? Okay, so it's the video quality is not very good. Shoot. Well, like I said, I'll work on debugging things on my end and see if I can figure out what's going on. Um, but this would be another simple example. So we can do things like figure out the magnitude of the normal force. Um, we can find the friction force. So in order to do that, we know that we need Oh, wait, wait, wait. Okay, sorry, this has got me all frazzled. So what I have here, this is just the weight. Now, if we start pulling on this, so this would not include the pulling force. If we start pulling on it, the sum of the forces in Y, we would have, in addition to the normal force, we have mg. So this would be 78 newtons in the J hat. Okay, and then if we want to find the friction force, that's mu k times the normal force. So that'll be 78, our 78 newtons times 0.3. And this would be in the negative I hat direction. Okay, so what else are we trying to find? We need to find the acceleration of the box. In order to do that, we need to sum the forces in the x direction. So what do we have? We're going to have the pulling force that's in the x direction, and then the friction force, which is resisting it. And that sum of forces in x is going to equal the mass times the acceleration in the x direction. So if we want the acceleration, we just divide by that factor of mass. And when we evaluate this, so let's see, 40 times cosine of 30 degrees minus our force of friction all over our mass, we find that this gives us an acceleration of 1.1 meters per second squared. And we could then turn off friction. If we turn off friction, we would lose this 23.4. And so we would just have Fp cosine theta over the mass. In this situation, we get 3.5 meters per second squared. Oh, and I should say this is in the I hat direction. So of course, it's going to be larger when the friction is turned off. And our situation that includes friction in court, it includes inside of it the case where we don't have friction. We can just make mu go to 0. And what was the last thing? The last part of the question is asking us if the coefficient of static friction was 0.5, would the applied force be sufficient to get the box moving? So I should say, let me just add in here. This was acceleration with friction. This is the acceleration without friction. And then this last part of the question, would the box move for a coefficient of static friction of 0.5? Well, we can figure out the force of friction. So we're talking about the static case now. So mu s times the normal force. So 0. 0.5 times our 78 newtons. Now that's going to be 39 newtons. And 39 newtons is larger than our FP cosine theta, which was 35 newtons. So in other words, the static friction can be larger can be as large or larger than our max than our applied pulling force. So the static friction wins, and the box wouldn't start to move. Okay. So yeah, sorry, are there questions? How are you guys doing? I think my presentation was pretty disjointed today. I was kind of frazzled with the stream not cooperating. Are there questions so far about any of the friction stuff? Questions? So here I can. Yeah, it is pretty straightforward. Yep, we're just adding another component in the x direction. Yeah, questions. What do you got? So I think I'll try later today representing this stream. I don't know why we had so many. Any chance we can see your feet? I don't understand that. Yeah, so you can imagine a variety of questions. Things like, um, you'd be asked to find the acceleration if friction was present, or calculate a coefficient of friction based on some given acceleration. Yeah, who is Min Wolves? Yeah, we might have a rando. So, if that should be an issue, we'll close the stream. We'll just make it unlisted. So, other questions about friction? So, I'll show you kind of looking ahead how this can. So, this is sort of the simplest situation. Part of what can make this more complicated is the fact that the friction will always uh, oppose the motion. So one of the homework problems involves a situation where you have a block that's initially going up an incline and then it comes back down. So in that situation, on the way up, the force of friction would be opposing the motion this way. And then on the way down, um, the force of friction would be this way. So since it changes direction, it can make things make your problems more complicated. So Okay. Um, we'll look at a more complicated problem next time, I think. And yeah, we'll figure out a way to deal with trolls here. Okay. Other questions? Appreciate your patience today, despite all the kind of technical difficulties. I'll spend some time seeing if I can track down what's going on with that. Um, sort of. Uh, yeah, looking ahead, we'll look at some more complicated problems. Other questions? So we can talk about questions in chat in Teams as well, um, or shoot me an email. Yeah, thanks for your patience today. Kind of a not ideal session. Okay, any questions? If there aren't any questions, we'll end the stream here. You guys have a nice day. Remember, no lab tomorrow, so we'll catch you on Wednesday. But I'll post some more stuff on friction today because we didn't get through as much as I was hoping. So.